So, what have been the surprises as we found all of these exoplanets? So, what surprises have arisen as we found planets around other stars? Well, right off the bat, with the very first planet, 51 Pegasi b, we had a huge surprise. A Jupiter sized planet with a 4-day orbit, that close to its parent star. Obviously, there's nothing remotely similar to that in our own solar system. That was a huge surprise. Scientists really didn't think you could have a planet that size that close. So that was a huge surprise early on. We've also not found many what you might call super Jupiters that are at least 10 times the mass of Jupiter. Now, beyond 70 times the mass of Jupiter, you're going to actually become a star at some point in there where you have enough gravity to ignite fusion. But scientists, I assume, were expecting more planets, these super monster planets that are just not there. And of course, this is something we should have a pretty good survey of because we can't actually find these things, and they're just not there. So there's a dearth of these where nature's just not creating these super monster planets. Now, starting with the second exoplanet ever discovered, 70 Virginis, we've seen planets with highly eccentric orbits. Our own solar system may be unusual in this regard because we have very circular orbits, just like the Earth's orbit is very close to being a circle. And so we're finding very eccentric orbits, which was a surprise. Here we just see a graph showing, this is a kind of an older graph, but showing the size of planets that we can find and their distance. And early on, at least, it was very weighted heavily towards really large planets really close to stars. Those are the easiest ones to find. But luckily, we've been finding smaller and smaller planets, and some of them farther away. So what is the Holy Grail for this field? Well, that's simple. It's find another Earth, an Earth-like planet. Now, that's very different than Earth-sized planet. You can have an Earth-sized planet that's right up next to a star and is completely inhospitable to life. Earth-like is what we want. And to know whether an Earth-sized planet is truly Earth-like, we need its spectrum. And so this wasn't done for the first time until 2009. It's very, very difficult to do. I'll explain why on the next page. But what do we look for in the spectrum of an exoplanet? Well, first, there's water, which seems to be the solvent for life. And certainly life on Earth is all reliant on water. Of course, other places might have a different liquid that they could use for life. But since we know water works and we know it's abundant in the universe, that's the first thing that we look for. We would also, if we found a planet with a lot of what you might call free oxygen, oxygen that's not combined with other elements, this would be key because the only way that's going to happen is if that oxygen is being replenished by things like plants and bacteria and so forth. Speaking of that, methane is another, it's a byproduct of life. If you've ever driven by a cow pasture, you know what methane smells like. And that methane, for example, there's been kind of a mystery on Mars the last few years where there's been kind of mysterious increases in methane. And some scientists have even speculated that could be from some kind of bacteria in the Martian soil, which is really fascinating. But again, that's the kind of thing that we would look for as a byproduct of life. Now, one of the future missions that's been proposed, I don't know what its status is, but the Terrestrial Planet Finder is what we'd really need to start analyzing these planets and taking photographs of them for the first time. And I'll get to that in just a second. First, let's look at how difficult this is. Here you have an interesting little picture here showing the spectrum of a star. That main beam of light and that rainbow, that's the spectrum of the star. But just the little sliver of light that bounces off the exoplanet right there, that's what we have to study. And that's why this is incredibly difficult. It would be like studying a firefly, a lightning bug, as it circled a lighthouse, and you have this intense beam of light that represents the star, but you're just trying to analyze the light from the lightning bug, and that would be incredibly difficult to do. And that's what this is like. It's just to separate that small amount of light, that small sliver of light from the starlight, which is overwhelming. So this is a picture of what this terrestrial planet finder might look like. This would be actually the spectrometer And then this would be, in order to take pictures, this would be kind of like 5 Hubble telescopes, let's say, working together as an interferometer in space. That's what it's going to take to really get good photographs of these distant worlds. Okay, the Kepler spacecraft isn't about taking photographs. It's about, as you may recall, looking for the blinks in starlight that as an exoplanet passes in front of a star, as it transits, there's a small dip in the brightness. The Kepler spacecraft watched one patch of sky for years. It's a patch of sky about the size of your hand held at arm's length. It watched that same patch of sky for years, and it was continuously looking at 150,000 stars. It's just amazing to think that there are that many stars in one little patch of sky just here in our area of our galaxy. That's kind of mind-boggling in itself. But of the 150,000, so far they have, I think it's now over 4,000 candidate planets. We'll go with the 3,600 here for now. Now you may think, well, that's a really small percentage of stars that have planets. But remember, for this transit method to work, everything has to be lined up perfectly. And we think that only maybe 1 to 10% of star systems would be lined up perfectly in order for us to find planets. We know we're missing 90 to 99% of planets. So, for example, this 3,600 on the low side probably represents 36,000 actual planets there, 36,000. And on the high side, we're talking 360,000 planets. I think it'll be closer to that in the long run, that we'll find when you survey 150,000 stars, you'll find hundreds of thousands of planets. This next part's almost a little depressing. Of the 3,600, only 45 of those planets were found in the habitable zone, the thin little ring around those stars where liquid water would be possible on the surface. And of the 45, only 12 were Earth-sized planets. Think about that. The Kepler spacecraft had to spend years looking at 150,000 stars just to find these 12 candidate planets, these 12 candidates to be Earth-like planets. It's pretty amazing. It's a lot of work just to try to find these. The first one that the Kepler team found that they could actually verify was a terrestrial world was Kepler 10b. This is a good example of a planet that is Earth-sized, but certainly not Earth-like. Look at that orbit, 0.84 days. That's how long it takes to go around its star, less than 24 hours. That's insane. Of course, it's going to be tidally locked and just completely roasted on one side. So far, the largest exoplanet system that we found is Kepler 11 with 6 planets. So our solar system still holds the record, but of course, not for long. Well, let's take a quick look here at some pictures. Of course, this is completely misleading. You go from Earths on the left to super Earths, and then you see Neptunes in the middle, Jupiters and super Jupiters to the right. But we can't find Earths and super Earths nearly as easily as we can find those large planets. So this is very misleading on the left-hand side anyway. I think we can conclude that it looks like we'll find a lot more Neptunes than Jupiters, and a lot more Jupiters than super Jupiters. I think we can draw that conclusion. But the rest of it, we're just not there technology-wise to really get a good survey of how many Earths there are going to be. But it gets better every month of every year. Here's that. At the bottom of the screen, you see the Kepler 11 system, 6 planets there, all in the same system. You see Kepler 10b there next to the Earth, just a little bit bigger than the Earth, and some monster planets there, larger than Jupiter. I'm going to continue here. This is the smallest exoplanet ever discovered, Kepler 37b. Now, it's incredibly close to its parent star, to its host star, so it's not a good candidate for being Earth-like, but that's pretty amazing. Now, Kepler 37d, as you see there to the right, kind of a super Earth there, that might be a lot more credible, although it's pretty close to its host star as well. The same host star. Here they are, the orbits there. Both of them probably too close there. But 37b, hard to believe it's actually smaller than the planet Mercury and just a little bit bigger than our moon, the tiniest exoplanet ever discovered. We've looked at some of this already throughout the chapter, the different methods for finding planets. Of course, we keep finding more and more, but these are the ones we're most interested in. One of these planets right here on the screen might be another Earth. We just have to be able to get the spectrum of their atmosphere and really analyze them. But it's really exciting to think that one of those planets could have liquid water on the surface and could have the first life beyond our Earth. Thanks for listening.